Hey, how you doing?
Good.
So today we're going to look at what happens when an electric charge is at a point in space in the region around it. So in order to get started, what is work?
Force times displacement.
Interesting thing about work, what we've been doing, that
Energy.
force times displacement is only for a constant force.
Uh-huh.
That equation, force times, is only if the force is constant, because the position is changing.
Mm-hmm.
If the force changes and the displacement is changing, then you have to use calculus, which we're not doing. So anyway,
Boo.
just a point, because that will come up later.
Mm-hmm.
What are the units of work? Well, units of force times units of distance, that's a Newton meter, which is a joule.
Mm-hmm.
And what's the work energy theorem?
Work changes energy.
It's simple.
Work
It's
is
a
the change in energy.
beautiful thing. Okay. What does the word impinge mean? It means touches, when it encounters something.
Uh-huh.
As an electric field hits a conductor, electrons flow in response. What the deuce does that mean? Well, here's a capacitor.
Mm-hmm.
Okay, here's a capacitor, here's a positive side, here's a negative side. Here's the electric field between it. If you put a metal ball in there, then electrons will be attracted to the positive side and repelled from the negative side. So they'll flow inside the conductor and leave naked protons on one side, which is positive, and negative on the other. So what you have inside this system, you've got the electric field goes from positive to negative, from positive to negative. So the field is interrupted, but picks up on the other side from where it came in. That works if it's solid or if it's a ring. Funny thing, inside the ring, there's no electric field. And another thing is, at the surface, the electric field is always perpendicular to the surface. It's a small deal. Okay, so these fields, due to an induced separation of charge, cancel out any fields on the outside. So you've got this external field which is going this way. On the inside, the field goes from positive to negative. That way, they cancel each other out. So inside, there's no electric field. All right. And electric field lines are drawn perpendicular to the surface. If you got a pair, if you have a charged pair, then the shape of the electric field around it will be like this, always perpendicular to whatever the surface is. All right. So if I lift a 7.5 kilogram bowling ball, 0.91 meters from the floor to the table, how much work did I do? Well, it's force times distance. What force am I working against? It's gravity. 7.5 kilograms times 10 meters per second squared times 0.91 meters. That's going to be 75 times 0.9. That'd be around 74, 73 joules of work. Okay. What happened to the work you did? Well, it's stored as potential energy in the bowling ball, right? Okay. If the floor is 0, how much gravitational potential energy does the bowling ball have up here? Well, it's
same amount.
73, 74 joules.
Yeah.
Whatever the calculation is. I'm too lazy to do it. Okay. Does Earth have a gravitational field?
Yes.
Yeah. Well, what is a field? A field is a region of space where forces are exerted. And here is a drawing of the Earth with lines of force, gravitational field lines, that are also perpendicular to the surface. You notice when you drop something, it doesn't go sideways?
Yeah.
So that's an example of the field around the Earth is always perpendicular to the surface regardless of where you are. All right. What happens to the force on a test charge when it's brought close to a point charge? Here's a point charge, there's an electric field around it. And here's my positive test charge. And what happens to the force on a test charge as you get closer.
It'll increase.
It'll increase, right, because of Coulomb's law, which we'll get to in a minute, I think. Would the force ever be zero? You'd have to get way...
Yeah, really, 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 really far
You'd
away.
have to go out there past Bakersfield.
Yeah, back to infinity.
Where infinity is. That's right. Okay, so here's Coulomb's law. And this is the originating charge.
A little blue guy.
And here's our test charge. Now, the test charge is always positive. It's just a convention. The originating charge, this looks like it's negative, though. To me. So, but it varies with the square of the distance. And what happens is this gets larger,
The force decreases.
this gets smaller, and it's not a geometric, it's an exponential decrease. So it falls off really fast. Okay? What would the force of a test charge be at infinity?
Be zero?
It would go at, that's where calculus comes in, is at the limit, as the distance goes to infinity, the force would go to zero.
Yeah.
Yeah. Okay. What would the graph of a force versus distance look like? I'm gonna use this blue one.
For a positive, for a negative. I know, I'm like, what
So
color?
here's force, and I'll just put position here. And at position 0, it's going to be its maximum.
Yeah, because it's going to be really close,
and then
right?
Here's that
Exponential.
asymptotic. He said asymptotic. Yeah. Okay. Wait a minute. What's this? Hang on. Shouldn't be that. Oh. What would the force on a test charge be at infinity? Well, it depends on this. If you have a negative charge, then oh, wait a minute. I've done this wrong. If I have a positive charge,
For your test charge, or for your originating charge?
if I have a positive originating charge, the force of repulsion would be greatest. So this would be for a positive test charge. So positive, this would be repel.
Okay, the force is the greatest when it's really close.
Yeah, so if it's a positive test charge, there's going to be a large force and it's going to be repulsion, right? What if it's a negative test charge?
It won't look the same? The attraction's going to be the closest?
Well, attract would be over here.
Okay.
And I actually should have this the
Oh,
other way
okay, yeah.
Because stupid. Okay, so if we have Q originating as negative, it'll be a mirror,
Yeah.
because when you get close to a negative, the force is going to be attraction, and then as you go out towards infinity, it falls away to zero.
Yeah.
How are we doing? We okay?
No, that makes sense.
Okay. The electric field varies with the quantity of originating charge and the distance. And if you recall, the electric field is the force acting on a test charge divided by the test charge.
That's right. And the forces cancel and the Q prime cancels.
Yeah, and so what we get is K Q original over R squared. All right, so what would the intensity of the electric field be at infinity? Here we go with infinity again. All right, well, the intensity of the electric field, it's like the lines, the closer you in, the more closer the lines are, the more intense the field is. And what happens as you go out?
The intensity decreases.
Yeah, the intensity is going to be the same kind of thing. You're going to have because it's R squared, that is the letter R. It's R squared. As this goes to infinity, the electric field would go to zero.
Yeah, that makes sense.
What would the graph of E versus distance look like for a positive test charge?
Is it the same?
This would be X. So if we have a positive test charge, what's the direction of the field is out from the positive into the negative. So out from the positive, the number gets bigger when you're closer. Okay, so for a positive test charge, this is positive field, negative field for a positive test charge. Get something that looks like that. And you know what? Yeah, I'm doing it right.
So is it it's the same for because it's the same idea, right?
Well, remember what's varying here.
Yeah.
It's the force.
Yeah.
And I probably should have left this up here.
Yeah.
So the charge is staying the same.
And the electric field and the force are
And so the
proportional.
As the force gets smaller, then the intensity
Yeah.
of the electric field is going to get smaller.
Yeah. Okay.
Okay, well,
And
the
same
question
thing for-
is, what about a negative originating charge?
Same
Well,
idea.
the field is going to go in to a it goes out of the positive into the negative. So for a negative, it'll be a mirror thing like this. Yeah. How we doing? We all right?
Good. Yeah. That makes sense.
Okay. Work done moving a charge in an electric field is stored as electric potential energy. Okay, so if I have a negative and a positive test charge, negative originating charge, if I let go of this, it'll be like this. It'll fall towards it. Yes.
Yeah.
However, what do you got to do to
Gotta do work to get away. Yeah.
And what does that do to the potential energy?
It increases it.
It increases the potential energy. So low potential energy, it's like gravitational potential, bowling ball close to the floor versus up on, and then higher potential energy. Okay. The location of zero potential energy is arbitrary.
Okay.
You know, kinetic energy, there's zero if there's no motion, but potential energy is always relative to wherever you say it's zero. Okay. It's the difference in potential energy that matters. That's the difference in electrical potential or gravitational potential energy. The difference between the potential energy on the floor versus up here is 73 joules. However, between this and down in the quad, it's going to be more because it's a greater distance. All right, so it's the difference in potential energy, and here's electrical potential difference.
Yeah.
It's
So I was
equal
just
to the
thinking
work
about.
done moving a test charge in an electric field. And as you do work, apply a force through that displacement, it changes the electrical potential energy, which is like gravitational potential. And how much work you do depends on how much charge you've got.
Yeah.
If you've got a smaller charge, good stop there.
Thanks. I was like a goalie
Yeah.
defending.
For less charge, less work moving it, or less force,
Yeah.
less work, more charge, more force. Okay, and that is electrical potential difference. And it's the difference in potential energy from one place to another. The displacement you move from one place to another. Okay.
So going back, that's what you're talking about before. Our force has always been constant, but depending on what the charge is, the force can change. Is that what you mean?
And so that's why I made that statement. What's happening as you move that test charge in the electric field, the force is changing.
Yeah.
And this morning, you know, I was half awake. I started looking through this, and I got to, where the hell does this come from?
Yeah. Yeah. So
You know,
the
KQ. I mean, I can kind of see Coulomb's law in there, but where's this? How come this is?
Is it the
and what
distance?
it is, it's differential calculus. This
Oh,
is where
okay.
you have to, you know, where you have to integrate. No, it's you have to.
the derivative or
differentiate.
integrate.
Yeah.
Yeah.
The derivatives, and so this is a result of calculus where both the force and the displacement is changing. Okay, and it has to do with slope. Hell, that. Okay, so just take it from me that the electrical potential. Now, what does that mean? It's like gravitational potential relative to how far away you are from the Earth. And so this is the electrical potential for a point charge for a particular distance from the originating charge and I don't even have a test charge. This point in space, this point in space, that point in space. But there's something weird going on here. Where is it here? Oh, I don't have it. Okay. I gotta be careful here. Because at infinity, this is based on the work done bringing a charge in from infinity.
Okay.
So here's your originating charge, and here's your test charge out somewhere the other side of Bakersfield.
Yeah.
At infinity. Okay, and out here, the force is very small. Out here, the force is very small.
Yep.
And so then that force increases as you come in, and so the work done is based on
You're
the
gonna have to
idea that you start at infinity.
Okay.
All right. That's where this comes from, and you have to make that determination. But, okay, what would the graph of potential versus distance look like for a positive test charge, for a positive originating charge?
Wait, didn't we already do that?
No, we've got field force, electric field, and now we're going to do potential.
Oh, was the intensity. That's right. Okay.
So this is electric potential,
Yeah.
and I'm just going to use the word potential.
Okay.
And you can have positive and negative. And what we're playing with here, and I'm going to go on to this next slide. All right. So as R goes to infinity, the potential is low.
Is it linear?
As R gets close, it's large. So for a positive originating charge, it looks like that.
Oh, okay. So say it again. What you just said.
Okay, for the potential, which is KQO over R, at any point, if you're in close, small number for this, small distance,
Yeah.
large potential.
Okay. Yeah, that makes sense.
Okay, that's if you have a positive point charge. If you have a negative originating charge, and this is a negative originating charge, then the potential in close is nothing, right? So it's, as long as I'm using red, I'll do this. It's a mirror image. So it's that potential increases, becomes less negative as you go away, but so the thing is this the end of it? Yeah. So what we're going to do now is open up the physics book.
Sweet.
Looking at it this morning. Okay, and so you can think of this as here's a positive point charge.
Okay.
And there are spheres around it where the potential is the same everywhere.
Okay.
And since this is a positive test charge, if you're right here, close in, everything is going to have this value in a shell of that radius.
Yeah.
Okay, as you go farther
At point
out,
D.
yeah, as you go farther out, there's going to be a different potential. These are called,
So A, B, and C would all have the same potential.
yeah, everything on this would have the same potential, and it would be different from D, less than D.
Okay, that makes sense. I mean, it seems to make sense to me. Yeah.
Okay, and that whole idea of higher potential inside and lower potential outside is based on this.
That right there. Okay.
Yeah. All right. And here are two charges. That's a positive, that's a negative, and there's the electric field that goes out of the positive into the negative. And the relationship, the shape of these equipotential surfaces, it's always perpendicular at that point.
I see that.
And so what you're going to have is the positive is like a mountain, and this is like a hole. And there's a beautiful illustration in the mechanical.
I think I saw it. It was
in the
like, it was like,
universe. Yeah.
yeah.
And so here, if you've got let's say you've got a positive here and a negative here. So what you get here then is the potential is greater here, and then exactly in between the potential is zero because they cancel each other out, and then it increases.
Yeah.
So there's a three-dimensional model for this, and I don't have that. And so equipotential surfaces for a point charge look like this, but in a capacitor, so this is a positive, this is the negative side. As you got your positive test charge, this is an equipotential surface, and,
like
they're planes.
Yeah.
It all depends on the geometry,
Yeah.
and that's all there is to it.
Okay.